Um, it's a great pleasure for me to introduce uh, my friend and long time ago, and now is a professor, associate professor at Arizona State University, Professor Konrad. Konrad, I never got to pronounce correctly your last name.
R, just R.
Okay, Professor R, I guess. Dr. R got all his degrees in mechanical engineering from Georgia Tech, and he has been basically associate professor. He's been at ASU for several years now, and prior to that, he was a research scientist at MIT and as well as postdoc at National Institute of Standard. And he has co-authored over 75 journal papers in a relatively short period of time during his career. So with that, uh, Conrad, please go ahead, take it from there and tell us about your basically research.
All right, well, thank you very much. Sorry for a little bit of a delay. And again, thank you for the invitation. I'm very excited. Too bad it's not in person, but hopefully it'll still be enjoyable. So I'm going to talk to you today about a couple intertwined topic. And as you can see from my title of my talk, it's on soft thermal materials and systems, from kind of microscale engineering of materials to wearable systems. So let's right away jump in. And let's ask the question, right? Why would soft thermal materials and system be possible, interesting, and relevant? And another route, right? What are? So let's start off with the materials. Typically, when you think soft, you think a polymer, something like a silicone, maybe a paste, and you think thermally insulating. Over the last couple of years, there's been a kind of relatively new development where instead of making composites more conductive by addition of kind of hard particles, there's a trend to start to add liquid metals, which are inherently thermally conductive, and also you can think soft. And what's kind of neat, and I'll show you a little bit about that later, is that because you have these little droplets in the material, as you stretch it, the droplets stretch along with the material. Consequently, you barely stiffen the composite while also making it thermally conductive. So then you have sort of soft and thermally conductive material. And once you have that, right, there's a number of applications for these materials themselves, just sort of as pads. But once you have this, you can start thinking a little bit broader in terms of thermal sciences and heat transfer. And if you look at industrial applications and really anything used in technology, we always have kind of hard and rigid surfaces, right? So in a power plant, you have condensers, boilers, everything's metallic. You may have a movable system or something like in the car, there might be things that move components individually, but still all of them are hard and rigid. And then if you think a little bit more broadly about nature, right, there are a lot of very interesting and very efficient, in some sense, solutions. For example, you can think of a rabbit or elephant cooling efficiently with their ears, right? And you can think of ourselves too, where a lot of interesting controls over heat transfer and mass transfer are achieved with soft, flexible, and stretchable components. And this allows, for example, for things like phase or shape change to control it dynamically and so on. So with that in mind, right, this is kind of this bridge between the material itself and attempt to seeing, well, we have the material, and could we have some kind of a better performance, new applications in terms of heat transfer by employing these materials? So my group has looked at a number of these things. So we looked at sort of soft surfaces, right? So you can think of condensation, boiling, and it looks like boiling could be actually very interesting. And also contact with soft surfaces. So you can say, for example, finger is a good example of that. And then the kind of next step to that is let's take the material and let's make actual thermofluidic systems. So the one I'll mention today and we start working on is just a simple heat exchanger, right? You have a single stream heat exchanger. And once you have this, you can then start building up to even larger systems and things that might be helpful, right, in some sense. And here we have kind of wearable systems make most sense, right, because you need the compliance and you need the movability, and our bodies are basically a great example of where such material might be helpful. And the scope of that is really for where I live. Exposure to extreme heat is going to be is already and is going to be a major challenge in the next couple of decades. So finding routes to kind of understand this and deal with it is important. So in today's talk, instructions were not to go in depth in too much, right? Keep it a little bit high level. So I'll go over kind of the material aspect, transition to this soft system, and then talk a little bit about the wearable part with cooling. Hopefully giving something to enjoy for everyone in the audience. So let's start off with the materials. The first motivation for developing these is in the realm of integrated circuits. So if you look, this is a good plot that I think shows, right, kind of these trends in different aspects of integrated circuits. And you see, right, the transistors go up, so your computation power of your or ability of your laptop and computers has gone up a lot in the last 20 years. But what has stagnated is the amount of power that they use. And primary reason for that is thermal. You essentially cannot get the heat out of the chips, right? There's a stagnation in this. And if you were able to do that, which with a few tricks, the machine that you're watching this on could operate 30-40% faster. If you do a very simple calculation of this kind of simplified IC package that, say, Intel produces, you very quickly find that the major roadblocks for removal of the heat that's generated here in the integrated circuit is at the two interfaces, which in this industry are called thermal interface material, or TIM1 and TIM2. And this is between the back of the chip and what's called the integrated heat spreader. This is this kind of 1 by 1 inch metallic plate that you might see if you open up your computer. And then the second interface is between the backside of that and let's say a heat sink, or you may have a heat pipe here and so on. And this is the classical story, right? You look at the interfaces on microscale, there's a very limited number of points that the surfaces actually touch, right? And you have air in between. So what we're aiming at is filling up this insulating area here with some kind of material that's more conductive and reduces the contact resistance. So in the industry or overall, you'll see these kind of, I would say, 4 broad categories of TIMs. You may have a silicone grease with particles in it, and really no matter what they advertise, if you go and measure it, it's usually the conductivity effective one is below 2 watts per meter Kelvin. If you cross-link that, make a pad. That's attractive because it's easy in the assembly line to put these accurately, and it's not as messy. And these similarly, it's some kind of a usually silicone material with hard particles in it, and the effective thermal conductivity is usually around 2-ish. Classically, there's been things like low melting temperature thin films that were applied. For example, indium has a very high thermal conductivity, but you start running into a thermomechanical issue where this warps and can kind of break down. And more recently, liquid metals, so room temperature liquid metals, have been applied. And this is actually image from the latest PlayStation. and ASUS started releasing them. And this has been long coming, and this is really where a lot of industry is probably going to go in the future. And we'll talk about these guys, right? So they're typically gallium-based liquid metals, so it's some kind of a gallium, indium, and potentially tin eutectic. This is what one looks like if you just kind of put a droplet on it of it, and you can see my student's reflection in the lab. What's interesting about these materials that's different than, let's say, mercury, is that they very, very rapidly oxidize. For thermodynamic reasons, this is usually gallium oxide. And this shell, you see, this is 5 nanometers. It's somewhere between 1 and 3 nanometers. Typically, it grows a little bit over time, but not dramatically. And what this oxide shell does is make the adhesion of the material very, very complicated. So this is something I took many years ago. This is inside of an ion beam microscope. So I'm imaging with an ion beam. So each pixel forms electrons that you can image. And then I'm also removing a little bit of material. So this is liquid metal droplets kind of spread on the material. And you'll see as I'm zooming in, I'm going to break up the oxide here. And you see this dramatic behavior change in wetting when the oxide is removed. So the oxide was kind of pinning the droplets. And when you remove it, they return to their kind of natural state where they ball up. What's nice about the oxide is that you can very, very easily make stable nano and micro droplets of the liquid metal just by, say, ultrasonic and large droplet in something that has oxygen in it. And here's just an example of something we made in my lab. And this is, you see this bunch of little liquid metal droplets that have oxide shell on them so they don't merge. That makes it interesting to make composite with it. So some problems with the liquid metals. Well, number one, the oxide makes them annoying to handle and to apply, right? So when you're doing something in manufacturing, you want high repeatability and so on. But the liquid metal, depending on what you do with it, will be anywhere from this to this. And depending on how you make contact with the surface, it's going to be completely non-sticky, or you won't be able to remove it. Second part, it has kind of a moderate thermal conductivity, I would say, somewhere between 1 and 5 watts per meter Kelvin is the greases, right? So the liquid metal is better than that, but it's still far below what a classical indium foil would provide you. Because it's liquidy, if you apply it, right, and you have some kind of warping that happens in every chip when you cycle it on and off, it squeezes out, so you end up with hotspots. And then lastly, this is kind of what gallium is famous for, is gallium-induced corrosion or embrittlement, or alloying, depending on what you're looking at. If you ever want to feel like Superman, take a droplet of gallium, put it on an aluminum heatsink, wait a couple hours, and you can crumble the whole thing in your own hands. There's a video of this on YouTube. Okay, so how can you address these issues? Well, we need to start doing something with the liquid metal. So one approach is to try to make the liquid metal better itself. And the easiest thing is to add air, which also creates oxide. And this creates liquid metal foams, which we recently, in literature, this is relatively recent, right? Last year we published on this, and there was another paper a few months before that. And this is very simple. You take the liquid metal and you just stir it in air. This creates this kind of interesting material. You see this in the cross section. It has bubbles that have oxide around them, but it also has these kind of crumbled oxide balls. You can think of it as kind of a aluminum foil. If you crumbled it up, it's something like this, just on a very, very small scale. And it makes the material much easier to apply, has lower density, so cheaper. It's easy to dispense, but it reduces the thermal conductivity. And we described this recently, but really this is what manufacturers of thermal interface materials based on liquid metals have been recommending you do for years, and this is has been used by kind of niche gamers and so on. niche users. So you take a Q-tip, you stir around the liquid metal, and it actually makes a foam. And this is where you can kind of use it as a TIM. So second approach that we explored is adding high thermal conductivity particles. So we kind of then make a liquid metal matrix paste, or you can call it a grease. So when we first looked at this a couple of years ago, it wasn't obvious what to add because gallium alloys with so many things. So this is kind of an old plot showing rate of corrosion in millimeters into a surface as a function of temperature for different materials. And where you see that really the most resistant material, metal in particular, to gallium is tungsten. You have to go up to really high temperature, and then after a little while, you start corroding. It also happens to have a very high thermal conductivity, much higher than the liquid metal itself. So it's a very good candidate. Right, so we wanted to avoid this oxide formation, so we built a little cheap glove box, you can think of it, right, with nitrogen flowing through it, and we started mixing the particles with liquid metal. And to a little bit of our surprise, nothing happened. It was almost impossible to mix the two together. And you can see it much nicer using a technique I developed a couple years ago for kind of this in situ imaging with liquid metal behaviors, right? So this is inside of a FIB-SEM, so you have this electron beam, you have a little nanomanipulator with which you can kind of move particles and you can glue them to it, and you also have a gallium beam to potentially remove something. So here I had liquid metal, and like in the other image, I kind of made a hole in the oxide, and we can then have this tungsten particle and dip it in the liquid metal and kind of look at its wetting behavior in situ. So we're going and start seeing, right, we're starting to immerse it into the liquid metal, and the particle is completely liquid metal phobic, right? If we borrow some language from wetting associated with water. And you put it under, you take it out, nothing sticks, which explains why when you try to mix them, you don't form a continuous paste. But what we saw was really interesting. If we had kind of patches of oxide floating on the liquid metal, when we start dipping the particles into that, some of the oxide, you see here, when we took out the particles, starts sticking to the particle. And then in kind of the subsequent step, when we took that particle with the oxide patches and dipped it in the liquid metal and took it out, you start seeing that liquid metal starts sticking to it. Consequently, there's a shift where this oxide enables wetting of the material. So macroscale, taking advantage of this, was actually very simple. Instead of mixing the particles in nitrogen, we mixed them with the liquid metal in air, and we were able to form these very stable pastes. You can see tungsten floating in the liquid metal, and it has a bunch of oxide that helps this happen. So by controlling how much of the tungsten we added, we could go anywhere from this very from fluid right to a wet powder and anything in between. And when we measured the thermal conductivity, we saw that about 40% particles were able to triple the thermal conductivity of the oxide itself. We made a nice paste that was pretty easy to apply. And if you take a cross section, it's sort of particles, there's some air pockets, and the oxide that enables this mixing to occur. Here's a FIB cross section of this, right? See tungsten, air, and so on. So this was a very nice result. But there's some issues with tungsten. It's very heavy, so it's not a great candidate, for example, for a portable system or for something like your Apple Watch, right? If your TIM weighs as much as your watch itself, you probably don't want to use it. So instead, we developed a kind of new technique, and we're about to publish this, where we took a powder, but the powder it's a hybrid particle. Specifically, we have silicon carbide, and we grew a wetting layer on it. We use a metallic one, we use silver. And what that allows is for mixing of the two together without the oxygen, so without the oxide formation. So there's some benefits to that. And it increases the thermal conductivity. And you see kind of this is the silver coated silicon carbide, and this is after we wet it. If you zoom in, you start seeing these little rods. That's the gallium silver alloy, so it's clearly working. And with that, we obtain very similar results as with tungsten, where the thermal conductivity is about 55 watts per meter Kelvin, depending on the mixture. So this allowed us to solve the problems with applying of the liquid metal, making it more conductive and so on, but it still doesn't address the issue with the corrosion. So to do that, what you want to do is add the liquid metal to another material, so make a composite. This could be added to a silicone grease, or you can cross-link that to make an elastomer. And some folks have done that a little bit before us. In 2017, we started publishing on this in 2018. And you see essentially you have these liquid metal droplets with oxide on them, you add them, make a grease, or you make a pad, and this is kind of the cross-section you might expect. So it's easier to apply, there's no corrosion issues as far as we know, but it has limited thermal conductivity. If you're just adding the liquid metal with, really pushing the volume fraction of liquid metal to about 80%, you're saturated about 5 watts per meter Kelvin. What's kind of cool, Michael Bartlett and Konrad Rykaczewski showed that if you stretch the material, the droplets stretch along with it. So along this axis, you can maybe push the thermal conductivity to 10 watts per meter Kelvin. So what we've done actually is we took the materials that I described to you previously, right, where we have this liquid metal with particles floating in it, and then we process it simply to make hybrid particle that has a solid core and a liquid metal around it, and of course it has the little oxide shell to stabilize it. And we add those to the grease, then we compress it in a way that induces merging of these particles. So you can see kind of these are our particles, and you see when we remove the grease or around it, we form these conductive bridges. And with that, we're able to make very repeatably greases that have thermal conductivity of 10, right? So it's about 5 times higher than anything you'll find really in the industry. And this is the effective thermal conductivity. So this takes into account the contact resistance. And if you subtract that, we're actually at about 17 if the resistance is subtracted. Furthermore, these materials are actually really easy to apply, right? So this is where we're squeezing it out of syringe, and it's exactly like a grease you might have. With all of the liquid metal materials, you might see some kind of alloying with other things that you might have added, and it's not a real material, I would say. So with this kind of story, right, where we have the liquid metal that we improved by adding particles with it. We added the wetting layer kind of based on our insight from these in situ experiments. We saw that we need induce the wetting, right? We could do that with the oxide, which was very interesting. Or we can do it with this additional silver wetting layer. And that produces potentially a liquid metal paste with about 50 to 60 watt per meter Kelvin thermal conductivity. Which is a big improvement even over what is put into the Asus laptop or PlayStation. And on top of it, we probably wouldn't need a gasket because it shouldn't pump out. And it's getting closer to what I would say the indium foils would have. To get rid of the corrosion issue, though, we put it into a grease, and we have some results on making pads too. And you see here's a result where we made a pad a couple years ago, and you put it in between aluminum, squeeze it, heat it, nothing happens. But if you put gallium on or galveston for 5 seconds on the aluminum, it just corrodes it and embrittles it, and it falls apart. So far playing some tricks, we're able to push this thermal conductivity to somewhere between 10 to 20 watts per meter Kelvin. And we're doing some couple other tricks, and we're really getting to the level where these pads have thermal conductivity about 20 watts per meter Kelvin, which is what you really need to remove the heat efficiency from kind of the more powerful and powerful integrated chips these days. So there's still a lot of work to be done. We have a very good collaboration with Intel just down the street. So you have to look at durability, thermal cycling, and so on. But in general, I'm pretty confident we can make these materials that are elastomeric and in a way composites with pretty high values of thermal conductivity, right? This is comparable to steel, really. So now I'm gonna switch and move on to second topic, which is really now getting to taking these materials and not just using them as TIMs, but maybe as some kind of a thermal system. So per the mechanical aspects, right? So this is a nice plot that shows you the mechanical modulus of a material. Here, these squares are if you add solid particles. So you see as you add just a little bit of it, the modulus just skyrockets. The circles here are an example of what happens when you add liquid metal. And you see that the impact is very gradual until really most of your material consists of the liquid metal. And then these curves in between are sort of these hybrid systems where you add a little bit of liquid metal, a little bit of solids. So this is from Michael Bartlett and Carmel Majidi from a few years ago. So you have this kind of, when you plot it on a thermal conductivity versus Young modulus plot, you see that these elastomers with liquid metal kind of occupy a unique space, right? Where things can be very soft and also pretty thermally conductive. And our work really took it a step farther, right? We have even higher thermal conductivity, and we actually shown that we can go to very, very soft materials. People even put these in hydrogel. So you're talking about things that have Young's modulus on the order of tens of kilopascals. And the visual demonstrations are nice. I mean, this is one of these materials, and you see how highly stretched you can have it. So we thought, okay, well, let's try to make a system with this. Let's try to go beyond just conduction and see what would happen if we have a stretchable heat exchanger. So this is an old video that we have of kind of our first flow loop that is very rudimentary. This is all the insulation removed, and we're just getting started. But you see that we're flowing water to, this is the dark section here is the heated and liquid metal section. And we're flowing water to this, and at the same time, we're stretching it up to between 50 and 100%. So then you very quickly come to a question of how would you design such a heat exchanger, right? And in this case, it's just a heated tube that undergoes periodic stretching and relaxing. That's the simplest type of motion really we could think of. And it turned out that this is actually a quite complex question. So to take a stab at it, right, we designed this kind of elementary system. And what I'll talk about is just the first step in laying kind of a theoretical framework for analyzing these. And I'll present my results in terms of these kind of cycles. So this allows us to collapse data from actuators that were, or from the tubes that are moving very fast and very slow into one curve, right? So if you just kind of look at what I'm showing you, it's right, this is a cycling between unstretch and stretch for one that was moving fast and one that was moving slow. So the simplest way to analyze these would be if we could use our classical steady state equations that you open your undergraduate textbook, and this is how we analyze a heat exchanger. So we could call it a quasi-static shape assumption. Or in other words, we're trying to answer a question: when is device slow enough for actuated, so something that's moving, and static stretch to behavior to match? So at each point of the stretching, right, could we apply an equation for a heat exchanger with exactly that shape? And to proceed on that, we decided to use just scale analysis. We're thermal engineers, so we love that approach. So if you look at heat transfer, really the dominant timescales here are going to be for radial conduction between, say, cooling liquid and heating on the outside, right? And if you plug in numbers, this timescale is about 2 to 7 seconds. And then another timescale we have is the axial convection. So this, you can think of it as a residence time for a molecule that comes in and comes out. And that comes out to be on the order of seconds too. Now we need to compare it to some kind of an actuation timescale. So for that, we can use the period of actuation, really. And this is somewhere between, by varying how fast the device goes, we can go in between 16 and about 300 seconds. So our simple hypothesis was that we could apply this quasi-static shape assumption, or again, apply just equations that you have in your textbook for things that are not stretching, to analyze our movable heat exchanger, where when the characteristic heat transfer time scale is much, much smaller than the device shape change time scale. So since the two heat transfer timescales were about the same, we can just pick one of them. We took the conduction. So what we thought is going to be important is this ratio of the conduction timescale to the device timescale. To test it, my student Praveen spent 2 years learning how to cast these pretty complex devices, right? So we added a spring to it to act both as a heater and as a temperature sensor. So here's an example of what one of these looks like. This is clear silicone, and we have water dyed in red, so you see kind of that in the inside. And they're obviously very stretchable. To test it, we spent a lot of time building a very, very carefully calibrated flow loop that included that, right? I showed you that video where there was that stretchable section that is also heated through Joule heating with the tube. So typical results for the heat removed by the water look like this. And if you, right, so I have different rates of actuation plotted here, and also steady state data. So this was, we stretched it, we let the tube, and the system reach steady state, and we plot that. That's kind of our reference. If you clean it up and look at the extremes, you see some kind of a trend, but the data is a little bit buried within the error bars. So what we done instead was look at a little bit more sensitive metric, which was the temperature of the spring itself, which we could get through its resistance. And we done experiments for the tube being just made out of silicon and having about 20% of liquid metal in it. And the way we present the data, that you can collapse it all in for different experiments with these devices moving fast and moving slow, is by looking at the average temperature of the spring. And you see right away here that addition of the liquid metal makes an enormous difference. If we have just silicon wall, the average temperature is 95 degrees Celsius. And as you stretch it, the temperature will oscillate around that. If you add a little bit of liquid metal, this drops by 40 degrees, right? So just having a little bit of liquid metal helps tremendously. Okay, so this is the blue curve is stretched, unstretched, stretched, unstretched, and here you have the percentage of stretch. So here's just a plot of, as we start moving the device a little bit at a very slow rate, about half a millimeter per second, you start seeing a shift from the steady state temperature oscillation around the mean temperature, which is shown in this triangular brown curve here. You start seeing some kind of a shift in both the silicon and liquid metal cases. And you can repeat that, right? And as you do many experiments with a faster rate of extension and contraction of the pipe, you start seeing a trend more clear. There's a phase shift and an amplitude decay. This becomes much more evident when you start, let's say, plot the phase shift versus the device timescale. And you see that for the silicon device right here, and then for the liquid metal device, you kind of see this very clear trend. And going back to our original hypothesis, when you plot this versus the ratio of the device, of the heat transfer timescale, the conduction to the device timescale, all the data, and this is hundreds of experiments, each point is an average, collapses into one beautiful curve, which you can actually derive analytically to be very simple. The phase shift is equal just to the square root pi of the ratio of the two timescales. So this gave us a confidence that our, to answer our initial question. So when is the device slow enough for actuated and static stretch tubes behavior to match? So from this equation, right, we need to pick some kind of a threshold for the two to match, and we said, let's say there's under 2% deviation, and this occurs when this ratio is about smaller than 10 to the minus third. So this is, I would say, the first step in trying to look at these shape-changing thermal devices, and how do you proceed to analyze it, right? So if this ratio is smaller than what we found here, you can apply classical steady state analysis to kind of interpolate in between the different time points. But if you're above that, right, you're in a regime where you might need to proceed to more complex analysis. So this was a fun, just beginning of really analyzing these devices. It's an interesting topic. I have a couple of students working on taking this farther and building condensers and other kind of interesting devices with this. So with this, I'll switch from discussing right materials, kind of basics of these systems, and let's talk a little bit about this motivation and application for personal cooling. So here's data like compiled for weather, for the daily lows and daily highs from June to August temperatures at Phoenix Airport. So this is in the decade before I was born. You might have a daily high was about 105 plus or minus 5. And this hasn't changed that much in the last decade. But if you look at the daily low, so this is the temperature right before the sun, right? The coolest you have during the day. In the 70s, it used to cool down below 70 degrees, and really majority of temperatures were somewhere, between 70 and 80, maybe a little bit above 80. And if you look at last decade, that entire curve has shifted. It's almost always hotter than 70 degrees, and majority of temperatures are between 80 and 90 degrees Fahrenheit, right? I mean, this is a substantial, statistically valid increase. In addition, if you look at last year, which was extreme, right? The average went up to 89 degrees. And I mean, this is, right, this is the histogram is, tells the story, right? I mean, there was a period of about a month where it did not cool down at all below 90 degrees. It was miserable. A lot of this has to do with Phoenix the population skyrocketing from about 50,000 people to 5 million since World War II. And really that is driven by development of air conditioning. So, you have, instead of having fields, you have this giant thing of heat capturing concrete. But the trend is accelerating with the heating, and a lot of it now is not due to just the urban heat island effect, it's due to climate change. What is worrying, I would say, and is really worrying for me, is that if you look at different indices for when you have high risk of heat illness, this is the wet bulb globe temperature index. This is borrowed from my friend's lecture on specifically on kind of athletic events. When should you cancel it? So obviously, the drier you are, the better it is. But even if you look at dry condition, 10 to 20% humidity that you have in Phoenix, you start seeing that at 90 degrees, you're at moderate risk. And when you jump over to 95 degrees, you're already at very high risk. And we're in the region where we're oscillating around here. And in a few years, we're going to be always in this high risk category. And this is for many months a year. So the common strategy that everyone takes here in the summer is to do outdoor activities in the middle of the night. I go mountain biking at 4:30 in the morning. But last year, even that was tough for an extended period of time. And I started cutting down because it was becoming dangerous. So, with projection of climate change, we're going to be in this high risk category and potentially very high risk category the moment the sun goes up for extended periods of time. So this is not only true for Arizona, right? If you look at kind of projections on a global scale, see that depending on which kind of emission scenario you want to look at, there are going to be places in the world that are going to be above deadly heat threshold, and there are many ways to define that. For many, even for most of the year, right? So with that, right, one of the newer topics that I've been exploring in the last couple of years is this idea of, we can call it, cute name, cool future fashion, right? Personal cooling as part of social adaptation to hotter climates. So my pitch is that having clothing that just makes you sweat better, which is really what most athletic wear and so on does, is not going to be enough. So we need kind of additional boost in cooling, which can come from kind of traditional cooling garments. And if you try to buy one these days, they're not particularly good. You can get them relatively cheaply or more in a complex way. So we've had two projects on this. One was taking the materials that we have discussed and turning them into better liquid-cooled garments. So here's we're passing water through them, and this goes on the body. And the second one I've been exploring is evaporative cooling. So having an evaporative cooling vest that you put on and trying to make them better. So I thought a little bit of audience participation. Let's see if this works. And it works in Zoom. I have time to talk about one of these. So if you think you would like to hear about liquid cooling, personal cooling, maybe try to highlight this icon. And if you prefer hearing a little bit about evaporative cooling, maybe select this icon. If it works well in Zoom when I teach, I don't have much experience with this. Let's see if
sorry, I am not familiar. So how are we gonna identify? So you need to just put that icon in the chat box, or?
Yeah. If you look at say participants, there's this, you can raise your hand or do feedback. Let's see feedback now. So let's say if you want to hear about liquid metal cooling, how about you raise your hand? So it's something like this. Let me see if I can see you out in these. Anyone? Is this working? If it's not, I'll just pick one. Which one do you want to hear about?
Yeah, let's just like give maybe
5 seconds. Oh, okay. I see.
You see
raised hand. So this was raised hand was for liquid cooling. 1, 2, 3.
So, yeah.
It's I love in normal talks. I love audience participation. It's very hard to do through Zoom.
Well, that's a good thing actually. It's just that
okay, you know what? I see 5 hands for liquid cooling.
Well, I guess like if you ask for the other one, you might get 4. So
Okay,
And
so now
I
let's
don't know
turn
if
off
some of,
liquid cooling. Let's look at evaporation. Raise your hand if you want to do evaporation.
okay,
One,
I'm counting.
two,
1, 2, 3.
3, 4. Oh man, so close. 5, 6. I think actually evaporative cooling is winning. Yep.
Yeah, all
All
right.
right.
Let's go with that.
Pranif, you cast the deciding vote. Okay. Oh, I've seen other people do this in talks at it. At least wakes up people. And I promise I'm almost done. I'm not gonna keep you too long.
No,
So
I'd love
all
to
right,
hear that part.
so let's skip ahead to evaporative cooling. And this one doesn't take into account as many of these soft materials. When we talk about it, it uses hydrogels a little bit different. So first question, where does evaporative cooling work well? Well, about 1/3 of population lives in what is referred to as drylands, and there's about a 50% increase in the last 25 years or so, 20 years in that. So drylands are supposed to cover about 50% of the land. And if you look at, right, where you have different subcategories of dry, it covers also a lot of populations where you will need cooling and you will need cheap cooling, right? So maybe air conditioning is not as popular. So looking at things that you can do easily, like evaporative cooling vests, is worthwhile. Cheapest way of doing that is, for example, in the summer, I used to bike home about 2 miles, and it's, let's say, 150 degrees outside, but it's also 5% humidity. So I would take my cotton jersey or something like that, just completely soak it in water and put it on myself, and I would really feel cold until I got home. But the problem is that cotton only absorbs about 10% of its mass in water. So in that 10-15 minutes, my t-shirt would dry up. An alternative to that is to have add some kind of material to a vest, and this is something you can buy for $20 on Amazon. I have one of these. And it has more or less diaper material. It has a super absorbing polymer, right? So this makes a nice soft gel that can absorb about 100% of its own mass in water. So all of these things can absorb 1 to 2 kilograms of water easily. So pluses, there's thermodynamic advantages to using evaporation over melting, right? So another alternative you see for cooling vests that are very popular is you have some kind of waxy material or ice that you put in a vest and you hold against yourself. So if you look at melting, the amount of per kilogram, you can get about 330 kilojoules. This is the best, water is the best for that ice. Evaporation, in contrast, the latent heat for this phase change process is over 2,000 kilojoules. So evaporative vest with the same weight, right, should cool you for up to 7 times longer. However, that is not the case. If you do put together a simple model of that, in a realistic case, you see that most of the evaporated water does not actually cool you. So we have this kind of simple graph here. It's the heat transfer coefficient, so you can translate to airspeed that you're exposed to in sunny conditions. So you have a solar flux onto it. And you see the evaporation flux. And in typical conditions, you have in summer here, right, so over 40 degrees Celsius and a little bit of humidity. We take one of these darker vests that has a absorptivity about 0.7. We can then calculate how much of the evaporated flux, right? How much of the evaporated water actually went to cooling of the person that wears the suit. And it turns out that when you have relatively low heat transfer coefficient, natural convection, despite evaporating tons of water, you're actually still getting heated. And so lesson number 1 is in sun, moderate convection is needed to get any cooling, but about 85% of water is wasted, right? It goes to cooling of the environment, not of cooling you. And you see this is how much cooling you get, about 100 watts of you, but you're cooling about 1,000 watts. If you add shade, it helps, but not as much as you would think. you get, and what's interesting is that the amount of body cooling you get saturates very quickly with the heat transfer coefficient. So blowing harder or adding airflow, you lose more water, but you don't get much benefit out of it. So the second lesson is, even in shade, water is used efficiently only at low airspeed. About 60 to 70% of water is wasted. And this is important for a portable system. If I'm wearing 2 kilograms, I want that kilograms to go to cooling me, right? It's heavy and annoying. I don't want it to go to cooling of the environment. And really, because of this, the evaporative cooling is no better than these phase change materials. So simple solution that I propose to that is, well, we need some kind of a shade over the vest, right? That would reflect this the solar radiation and throttle the convection. So you can think of, kind of a design where you have louver shades or maybe slots over so it's a second layer over the evaporative cooling vest. And it turns out that the two of these work about the same, about as well. So I'll just focus on this one. And we'll talk about two flow conditions. One is not moving, no wind. So evaporation is due to natural convection. And here, this is actually more complicated than just regular natural convection, because humidification of the dry air changes the density of the air as much as cooling of it. So you have these two effects on buoyancy. So you have to simulate both the fluid dynamics, the temperature, and as well as the mass transfer. So it's much more complicated than just natural convection, thermal natural convection. So the second condition we'll talk about a little bit more of forced convection. So first, let's look at the slitted shade design under natural convection. So we'll have the vest, and the body is on this side, and then we have some of a gap between the vest, and then we perforate it. So if there's no gap, so it's the shade sitting directly on the vest, you get some kind of a flow field that looks this, and this is the temperature field up here. And what you start seeing is that as you add a gap, the flow around, in between, and also around the vest increases a lot. And you can plot this, right, as a function of the spacing of the vest and the gap. And this is the evaporative flux. And you see that it saturates at around 15 millimeters. And this is in this area of garment design. This is known as a ventilation gap. So similarly, if you're wear a raincoat or a ski jacket, you feel much better if there's a little bit of a gap and air can move. Same happens for Bedouins in the desert. They wear loose clothing. So then you can also calculate the body cooling flux, and you start seeing that it also saturates. And you can play around, right, with the number of slots, and in this case, the more you add, the worse you kind of get. So number one lesson is we want a ventilation gap for optimal cooling in natural convection conditions. But what happens if you have this gap and kind of these slots when you all of a sudden start having forced air convection, right? So in this case, you have airflow coming at your base with your gap. And it turns out that almost no matter how many slots you have, then if you have this gap, right, air comes in and moves along, right, and it comes out somewhere around the neck or somewhere around there. And it doesn't matter how many you have. You go back to the same problem that we had initially, where you're wasting a lot of the water because of environmental losses. So you don't want a gap when you have forced convection. So what you can do instead is try to collapse the gap, right? So here the shade goes onto the vest, and in this case, when you plot, you see that by changing the number of openings, right? So essentially controlling the evaporative area, you can throttle the evaporation to whatever rate you really want. So with that, right, solution that I proposed in this paper, and we have a patent on it, was to have a collapsible wind shade. So in low wind condition, when nothing presses on it, it pops off, right, and it has this ventilation gap. But when you have some kind of air movement, it collapses the shade onto the surface, and then this way you control the evaporation rate by controlling the number of slots. And if you play around with it, theoretically, you can get some kind of optimal size and number of slots. You can get about 100 to 200 watts per meter squared cooling, irrelevant if you're exposed to sun or wind and so on. So this is not going to help you, run a marathon, but if you're doing moderate activities, if you're doing construction or a walk or maybe a slow jog, this will provide you with enough to really augment your thermoregulation. And on top of it, around 50% of the evaporated water is actually used for cooling you, right? Versus say 50% without the shade. So that, I'm going to conclude. I think this is what I've talked to you is really making current cooling garments better. But I think in future, right, we might need to rethink the kind of purpose of fashion, right? From aesthetic maybe to cooling function. If you're interested, I wrote the editorial on this a couple of years ago. So there's all sorts of crazy looking fashion that's proposed, right? The question is, could we use it for something implemented for cooling? And the argument I also made, right, if we convince people were convinced that something was pretty cool to wear, right? Fashion is cyclical, so maybe 100, 200, 300 years ago, if we think it and it actually ends up being a cool design for cooling, we might be able to reuse it and convince people that this is needed. And people have been actually thinking about this in different times. This is an article from 100 years ago that talks about the need for men to stop wearing winter clothing in summer, which was at the time they thought it was cooling. So people have thought about this in different times and so on. So right, so this is the end of my talk. So I hope it was interesting. We talked a little bit about making new type of materials that are soft and thermally conductive. Then we talked about implementing them into a stretchable thermofluidic system or heat exchanger. We talked about how you would go about starting to analyze these devices. And then lastly, we talked about wearable soft thermal systems, which are really personal cooling. And we didn't talk about applying the pipes on the body. If you're interested, we have a paper on that. We picked the evaporative cooling, right? So I don't do this by myself. For the materials part, I have a great collaboration with Robert Wang from ASU, and we co-advised many of the students that worked on this. Here are the students specifically that worked on the subjects that I talked about. Lots of doctors, so lots of guys and girls that graduated recently. The funding was from Semiconductor Research Corporation to NSF grants. And then lastly, from I talk about the cooling garment design. I mean, so far it's kind of theoretical or lab scale testing. We really have a great team of people who are interested in human heat exposure and urban heat island effect research at the ASU. And I'm spending most of my time these days trying to organize a kind of state-of-the-art or probably very unique and one of the best laboratories in the world for studying this indoor and outdoor. We have this what's called the Global Futures Laboratory in the new building that's getting built, where we're going to have a human biometrology lab, and I'm trying to organize a couple of instruments that are really interesting. So if you're interested in this topic, in the next couple of years, we really are going to have a lot more coming out of it, and hopefully some solutions to making it a little bit less miserable here in the summer. So with that, I'll be glad to take any questions.
Thank you very much, Konrad. Very interesting applied research. Hopefully get to wear one of those garments.
Yeah, I mean, you have to work on something locally relevant. I think icing is great for Toledo. For Arizona, it's the heat. This is actually a picture of me mountain biking. ASU is here on the bottom, and you see this is my mountain bike, and I've been on the mountain already for about 45 minutes, and this is just the sunrise, because otherwise it's just, man, it's tough in the summer.
So questions for our speaker. If you have questions, I know we went a little bit over time, but
yeah, I was sorry for the.
No, it's all right. I'm just using my laptop and not double monitoring. So Mohammed Shams was thanking you for the presentation, and he was saying that I was just curious, what could we use this material for the car engine too? Can we use this material for the vehicle engine, I guess?
Yeah, I mean, you have to look at temperature limitations and so on, but silicon's good until about 200 degrees Celsius, so that might limit it in combustion. But if you play it, if you add, it depends where, I would say. And it's still very, very early on. I think I'm one of the first people to try to even probe this area and think about it. Unfortunately, mechanical engineers are fairly often behind electrical engineers. So people have been doing soft robotics and for years, but no one has thought about soft thermal systems, I think, in much. So maybe, but I think the part that's exciting is we don't know. I mean, it adds a whole new dimension to how you would design a system, how you could control it and play with it. That's very interesting. And again, it's used a lot in nature, right? To do I mean, you're a great soft heat exchanger. That's how your body regulates, right? How much heat you're losing from your body is by expanding and contracting capillaries in your skin.
So I have another question from Hakeem. He's trying to see if you guys have tested these materials, these vests basically inside of a washing machine. Uh, can they basically handle going through the cycles of?
Yeah, so a lot of them have been, and the ones that you can buy commercially. We haven't gotten to that point. This is the stage where I say, this is still for me very early in this area, and this is where we're trying to build up a laboratory to test this systematically, and then move on to more applied questions like that. And we do actually have the fashion department on board, and there's people who. So it's very interesting trying to organize proposals with anyone from geography, engineering to fashion to collaborate in the same space. It's because you have to also make things people would want to wear and are comfortable to wear. You have to worry about a lot of how would it rub your skin and cause irritation and so on. So it's very interesting area to work in.
Right. So I have, we have a lot of audience that, in our department, they do additive manufacturing, 3D printing, and in general, basically making pieces and parts. So I was looking at these soft thermal interface materials, and I assume that they're like non-Newtonian fluids, right? So when it comes to somewhat basically building parts or basically trying to use like these conventional methods that we have for uh, basically making pieces or parts that these materials could be used. Have you guys looked at the rheology of these things? Have you guys looked at how in manufacturing processes these could be applied?
Very important aspect, very good question. Here and there, it depends on what. We've looked at the foams, at the viscosity, and in some cases of the greases. In general, it can be very complicated because you have the liquid metal, the solid, the polymer. There's non-linear transitions depending on the rate. It's very interesting. So we're just starting to probe that. I have a new grant with Michael Dickey from NC State on these foams, and we're really going to tackle the viscosity in that aspect. But you can 3D print these things if that's kind of one of the questions. There are examples, and we've done a little bit of that in my lab. We haven't made parts with that yet or anything too particularly useful, but I think that these materials in general, there's such a possible, I would say, library of materials that you can make with it that you can tune it to be 3D printable.
Yeah, definitely that's going to be opening up a lot of new areas for applications of those materials.
I mean, learning how to cast these materials, in a tube even, it takes a while. It took my student about 2 years to make these well.
Wow. Well, I'm just going to ask the audience for any. I know we ran about time, so so let me see. We have if you guys could put in the Q&A. I see another question, but it's in the chat. In the future, Praneet is asking this question. In the future, will it be possible to make a variable capacity heat exchanger with these soft materials where we can increase the cooling capacity based on demand?
Sure. Yeah, and this is the topic I didn't talk about where we have the liquid cooling. That works perfectly with that. So we're one of the grants I keep on trying to get funded is combining this material and development of the system with wearable uh, sensors that can estimate how much cooling you need, right? So they can look at your metabolic rate, estimate from your heart rate, and use artificial intelligence to kind of spit out the number of watts we need to remove. And based on that, we address it. And we also combine it with hydration. So that's another big aspect is people get fairly often dehydrated. So they, and that spirals down and there's a cascade of events where you get more and more prone to heat illness. So we're trying to combine this kind of system that tells you how to drink water and gives you cooling when you need it. And it gives you the right amount. So
Sounds good.
with liquid cooling, it's easy. You pump more water.
Okay, so any other last minute question or comment? And guys, we have our speaker's email in that file, that the share file. So if you have questions or comments, you might contact our speaker as well as usual. Um, so if there's any other last minute question or comment, please let me know or put it here. Yes. I don't see any. I guess that basically, given the time, that concludes our talk. I'd like to thank you again, Conrad, for a very interesting applied research. I think you have adjusted very well to Arizona in terms of making your research very useful over there.
Yeah, icing is not. I mean, I actually have a picture here of this was a couple weeks ago where like once a year I see snow from far away.
Right.
Other than that, we had some projects where we look at rattlesnake drinking, but I skipped since I ran over time. I skipped it. But it's
Sounds
yeah,
good.
icing is not. It's hard to get motivated here for icing.
Of course.
You guys want to have a two-minute video on this research we did on rattlesnakes, but it's okay. I'm
Yeah.
glad to share it later.
Yeah. Okay. Thanks everyone for joining. I appreciate it. So I think Conrad, do you want to do you have a few minutes to stick
Yeah,
around or
absolutely.
right? So
I have time.
okay, I guess if you know if everyone you guys are feel free to disconnect. So it would be great if we could have you in person. Unfortunately, this thing is a little bit tricky now, but hopefully
It
in
is. It is. I very much appreciate the
yeah,
invitation.
in
So,
near future, yeah, in near future, we can basically have you visit us. So we basically have the reason I was asking that question, we have a lot of basically faculties and students. They're doing research on manufacturing and making pieces and parts, and looking at those basically printable basically materials in general. So that's why it would be interesting for some of our students doing research on that.
yeah, I hope this was a good. I tried to touch on a lot of different aspects that people might be interested in and around. So
Sure, sure. No, it was very interesting and great to see all these things. So I think you've been at ASU for like how 7 years maybe or more?
almost 8. Yeah, it's
8.
been.
Wow, that's
Yeah, my wife. I don't know if you know my wife's a professor here too.
yeah, yeah. You told me that like in the
Yeah, so
business.
we're um yeah, a lot has happened. A lot of 2 kids running around, which you probably could have heard, and last year's been interesting. Both working from home, and for 5 months we tried to work and take care of them ourselves, which is
Right. I don't
quite
know how.
something.
Yeah,
Do
that's
you do,
fine.
do you have kids or no?
Not yet. No, no, not yet. So yeah, I've been here like 4 years, but I just it was just not that long ago that in the APS meeting in Boston, I'm like, you were just telling me that you just started. Uh,
Yeah,
it was,
time goes by. So you got a year till you applied for tenure.
yeah,
So
yeah, yeah.
well, you seem to
So
be doing very well. So
yeah, yeah. So it's like a lot of things that we do. It's just like for the demand related to now that these issues in Texas happen for the wind turbines and power generation. So we're going to look back, yeah, the same, we're going to look back at those things, mostly working with companies on wind turbines, solar panels, um, a lot of autonomous driving for basically um, camera lenses and etc. for preventing snow, dust, basically, or ice or anything to accumulate on the camera lenses. So um, it's mostly, yeah, energy and transportation sector.
yeah,
We
man, I mean, I like industrial funding because well, it it can be a little bit more demanding than
Yes, it is.
NSF, and NSF money is lovely, right? But industrial is nice because it shows you that people care, right? There's
Yeah,
actually because there's just so many papers published these days on things that are just filling up the library, right? And I've done plenty of that, but I enjoy. I mean, the best project is where you do something fundamental and at the same time you do something applied with that, right? That
sure.
is like the nicest part. But I think it's and that was the biggest part for me for the surface engineering was I I wasn't the person that could make them last long, right? And that I reached, I think, the point where I was done exploring the physics to the point where I was happy. And then the next part would have been something that I don't have that much expertise in. So I at the time started shifting, right? And other things happen. And I think this area with the cooling is locally relevant, and it's a big like global issue coming up, and we have a great place to do the tests, right? So that's like employing the local resources. It's last year it was for almost 6 months a year, it was hotter than 100 degrees.
Wow. Yeah. Yeah. You told me that it was, yeah, it's those numbers, both in terms of the, getting icing and snow events and those kind of temperatures in some areas that people didn't expect, plus extreme high temperatures and all these irregularities. They are all climate change, and hopefully, we're trying to address these things in a smaller scale, but I hope that in a bigger scale, things move in the right direction so that,
Yeah. But I mean, almost
it's
no matter what gets done, it's almost guaranteed that at least this century, there's still going to be many decades where we're going to feel the effects, right? And depends. My kids will. We'll see. I started thinking about like a lot of the end limit projections are like 2100. I'm like, man, my kids will be still around.
yeah.
Right? It's one of those things like I don't know if I'm probably not gonna make it, but it's interesting to think about it that sense. But yeah, no, it's been good. And it's funny because a lot of the stuff I'm doing actually builds on the wedding, and we might have